Welcome to this explainer. If you're the kind of person who loves to peel back the layers and figure out how everyday things actually work, you are definitely in the right place. Today, we're diving into the hidden mechanics of food quality, safety, and, believe it or not, industry economics. We're talking about something so common, literally everywhere, that we completely take it for granted, yet it dictates the physical stability of almost everything we eat. Yep, we are talking about the science of moisture analysis. Stick around because what seems super simple on the surface actually requires a mind-blowing level of scientific rigor behind the scenes.
Let me just throw a quick question out there for you to think about. What is the single most economically important ingredient in your food? Go ahead, take a guess. You're probably thinking, I don't know, expensive spices, high-grade proteins, maybe some complex preservatives. Actually, scratch that. It's way simpler and honestly a little surprising. It's water. Literally just water. It is the invisible, universally abundant, and insanely cheap filler hiding right there inside our food. And for food processors, man, water is both a total blessing and a massive headache. Since it's a cheap filler, there's a huge economic incentive to, keep it in there. But because it completely dictates when food spoils, food scientists have to masterfully, and I mean meticulously, control it. Okay, let's dive into this. Here is our roadmap for today. First, we'll hit the hidden value of moisture. Then we'll look at standards, quality, and preservation. After that, we'll check out the 3 states of water, the science of sampling, and finally, we'll put it all together with the cheddar cheese test. Let's get to it. Starting off with Section 1, the hidden value of moisture and its economic impact. So, in the food industry, running a moisture assay, testing for water, is absolutely fundamental. But surprise, it is notoriously difficult to get right. To understand why, we've got to define our baseline term here, total solids. What are total solids? It's simply the dry matter that's left over after all the moisture has been sucked out of a food product. Remember how we just said water is a cheap filler? Well, that makes total solids a metric of massive economic importance. Think about it. If you're a manufacturer selling a product by weight, every tiny fraction of a percent of water you can safely leave in there is essentially free weight. On the flip side, if you're the one buying raw ingredients, you want to make sure you're paying for the actual product, right? Not just a bunch of excess water. Because of this dynamic, scientists need a way to compare apples to apples, sometimes quite literally. This means we have to look at a dry weight basis versus a wet weight basis. If we want to uniformly calculate the nutritional value of a food, or say compare lab data across a bunch of different batches of a product, we absolutely have to know the exact moisture content. By converting measurements over to a dry weight basis, we basically strip away the whole water variable. It's a game changer. It lets scientists express their results on a completely uniform, standardized baseline, no matter how wet or dry that specific sample happened to be when it came into the lab. Moving right along to Section 2, Standards, Quality, and Preservation, Regulatory Frameworks. Now we're shifting gears from just raw economics to the actual, literal laws that govern our grocery store shelves. Take a look at these standards of identity. These are legally binding compositional standards, no joke. If you want to sell cheddar cheese, legally it must contain 39% moisture or less. Enriched flour, capped at 15% moisture. And if we look at it from the total solids perspective, pineapple juice has to hit at least 10.5 degrees Brix of soluble solids, and glucose syrup needs a minimum of 70% total solids. These aren't just polite suggestions from regulators. They are the strict, required parameters that define what these foods legally are. But these standards don't just exist for the sake of economics. They are quite literally the ultimate defense against spoilage and degradation. Moisture is a massive, massive quality factor. For instance, strictly controlling moisture is what stabilizes dehydrated vegetables, dried milks, and powdered eggs. It's what stops them from turning into a science experiment in your pantry. In stuff like jams and jellies, nailing the exact moisture level prevents sugar crystallization, keeping that smooth texture we all love. And reducing moisture is an absolute necessity if you want to ship things efficiently. Think about packaging liquid cane sugar. They concentrate it down to 67% solids. Corn sweetener, a whopping 80% solids. Moisture tests even determine exactly how much water has been added to processed meats. So yeah, controlling this invisible ingredient is literally everything. All right, Section 3, the 3 states of water, the molecular level. To truly control water, we really have to understand it first. And water isn't just simple wetness. It actually exists in 3 very distinct forms in our food, and how it exists completely dictates how easily we can extract and measure it. First up, we've got free water. This is pretty much exactly what it sounds like. It retains its physical properties, acts as a solvent, and disperses colloids. It's relatively easy to coax out. But then we run into adsorbed water. This water is holding on tight. It's occluded in cell walls, in protoplasm, and fiercely bound to proteins. And finally, there's the water of hydration. This is water that is bound chemically at the actual molecular level, like you'd find in lactose monohydrate. Because water loves to hide in these different states, a moisture test might measure more or less of it, depending entirely on the specific technique you use.
And because of all those clever hiding spots, there's rarely just a single universal way to measure moisture. Multiple official methods can exist for the exact same product. For example, if you check AOC International, the official methods for analyzing cheese include using a vacuum oven, a forced draft oven, a microwave oven, and distillation. Wild, right? Basically, the ease of water removal dictates which method you use. Now, while the first method listed by AOC is usually the go-to, a food scientist has to pick the exact right tool for the job. You have to draw out those stubbornly held water molecules without completely destroying the rest of your sample in the process.
Which brings us to Section 4, the science of sampling, handling precautions. So we've talked a lot about the theory. Now, let's get into the lab. Sample preparation is an incredibly sensitive operation. In fact, it's probably the greatest potential source of error in the whole process. Because of this, scientists have to treat sample handling like a strict, unforgiving operational checklist. Step 1. Any exposure to the open atmosphere must be kept as absolutely short as physically possible. Step 2. When you're grinding a sample up, you have to be super careful not to heat it by friction. Why? Because that heat causes moisture to evaporate before you can even measure it. Step 3. The empty headspace inside your storage container, gotta keep it to an absolute minimum so the sample doesn't lose its moisture to the air trapped inside the jar. And Step 4. Temperature fluctuations must be fiercely controlled. You see, moisture will actually migrate inside the container right toward the colder parts. If that happens, a scientist literally has to remove the entire sample, blend it all up again super quickly, and grab a brand new test portion just to get an accurate reading.
Finally, Section 5, the cheddar cheese test, precision in action. Okay, to really hammer home just how insanely fragile this whole process is, I want you to imagine we're weighing a sample of shredded cheddar cheese. We're talking just 2 to 3 grams of it, sitting in a tiny aluminum foil pan on a highly sensitive analytical balance. What is truly shocking here comes down to a single number: 5 seconds. In a laboratory study analyzing that tiny sample of cheddar cheese at an ambient 50% relative humidity, it took a mere 5 seconds for the sample to lose 0.01% of its moisture to the surrounding air. Just 5 seconds. Before the scientist has even finished writing down the weight, the water is literally vanishing into thin air. When researchers actually plotted this out, the results were pretty striking. Tracking that 0.01% moisture loss at 50% relative humidity, it takes just 5 seconds. Bump that humidity up to 70%, and the time doubles to 10 seconds. Now, you might intuitively expect this evaporation to happen on a curve, right? But the study showed this moisture loss was actually a straight line, linear function over a 5-minute interval. This linear vanishing act happening right there inside the balance proves the absolute, non-negotiable necessity of speed. You need strict environmental control during sample collection and weighing, long before the actual drying and measuring process even begins. Which leaves us with a pretty provocative thought to consider. If an invisible ingredient like water can just vanish from a highly controlled laboratory scale in a mere 5 seconds, how tightly are we really controlling the hidden economics, the strict regulatory standards, and the physical stability of our massive global food system? It really highlights the incredible, often unsung precision required by food scientists every single day. So the next time you're checking a nutrition label, or you notice the absolute perfect texture of a jar of jam, or hey, even just enjoying a slice of cheddar cheese, remember that invisible, meticulously measured dance of moisture that makes the whole shebang possible. Thank you so much for joining me on this explainer, and keep asking those big questions about the hidden mechanics of our world.